Right Academy. Learn it, teach it, remember it. Heaps. The secret to keeping the champion on top. By the end of this, you'll read the smallest thing off the very first slot instantly with no searching at all. It's already there waiting for you. Forget the word heap for a second and picture a knockout tournament. Players are arranged in a bracket, and in each match the smaller number wins and rises. Pair by pair, the winners keep climbing higher. At the very top sits one player who beat everyone, the champion, the single smallest. To find it, you don't search, you just look at the top and it's already sitting there. Now imagine a tournament that never actually ends. New players keep walking in, and every so often the current champion leaves. The field resettles to find the next smallest, and here is the real magic. It costs almost nothing, not a rerun, just one short walk up or down a single path. We'll keep the smallest on top throughout, and that's called a min-heap. A max-heap is the mirror image, largest on top, and every single rule flips. So learn one of them, and you've quietly learned both. Here's how a heap really stores that bracket as a tree with each parent sitting above its children. But not just any tree, because every level is completely full. The one exception is the last level, which fills neatly from left to right. No gaps are ever allowed, and we call that an almost complete tree. So why insist on that exact shape? The first reason is that it stays beautifully shallow. Double the number of items, and the tree grows by just one more level. The height is the logarithm of the size, and that height is the length of every path we ever walk. The second reason is the beautiful part, because the rigid shape lets us throw the tree away. We draw the usual child pointers, and then we simply discard them. The nodes drop straight down into a plain, flat array. No pointers, no node objects, and we lose absolutely nothing. You read the tree like a book, top to bottom and left to right. The root lands in the first slot, and a blue token traces the reading order. Its children go in the next 2 slots, their children in the next 4. Because there are no gaps, the array is packed completely solid. Now watch the slots very carefully. The children of slot 1 sit at 2 and 3. The children of slot 2 sit at 4 and 5. And the children of slot 3 sit at 6 and 7. So the children of any slot are double it and double it plus 1, while the parent is the slot halved. The tree was really an illusion, just a flat array and 3 little pieces of arithmetic. Most code counts the slots from 0, so the formulas shift by 1. Children sit at twice plus 1 and twice plus 2, and the parent at 1 less halved. It's the same idea exactly, so just pick one convention and stay with it. Here is the one rule, and it's honestly the only rule. Every parent is smaller than or equal to both of its children. You apply it at every single node, all the way down. Now notice what the rule does not say. It does not say the array is sorted. It does not say the left child beats the right since siblings have no order. It's a purely local promise, just each parent against its own kids. And yet that weak local promise has a powerful consequence. Walk any path downward, and the values only grow. So the smallest cannot hide anywhere below because that would break the rule. The minimum has nowhere to live except the very top, always. Suppose you add a brand new number. The shape has to stay almost complete, so there's exactly one legal place for it. It's the next open spot on the bottom row, which is simply the end of the array. But the rule might now be broken since the newcomer could be smaller than its parent. So you simply ask, are you smaller than your parent? If so, you swap, and the value bubbles upward past every parent it beats. It stops when a parent is smaller or when it reaches the root, and that is sifting up. And notice what sift-up quietly leaves alone. It only ever touches the chain of ancestors above the newcomer. Every other branch was valid and stays valid, so it's one narrow path, and that locality is why heaps are fast. Let's build a heap for real, inserting these numbers one at a time and sifting up after each. 5 goes in first, and since the heap was empty, it becomes the root. 3 goes to the end, beats 5, and swims up to the top. 8 goes to the end, does not beat 3, and simply stays. 1 goes to the end, beats 5, then beats 3, and climbs 2 levels to become the new champion. 9 goes to the end and just stays put. 2 goes to the end, beats 8, then stops just under 1. And notice, the array is not sorted, yet the minimum sits right on top. Finding the minimum is completely free because it's just the root. But usually we want to remove it, and we can't simply pluck it out. That tears a hole, with 2 candidates fighting to be promoted. So here's the trick. Take the last element and move it up to the root. The array shrinks, and the shape stays perfectly intact. But that interloper is far too large, so the rule is now broken right at the top. We repair it by pushing the interloper down, the exact mirror of sift-up. And here's the small detail that people get wrong. You compare against the smaller of the 2 children, not just the left one. Only the smaller child can rise above its sibling without breaking the rule. Swapping with the larger child just breaks it all over again. So you find the smaller, swap, and sink until it's smaller than both, or it hits the bottom. Let's extract twice from the heap we just built. The minimum is 1, so we set it aside and move the last element, 8, up to the root. Its children are 3 and 2. The smaller is 2. 8 beats it, so they swap, and 8 sinks down and stops. The new minimum is 2, and that is the answer the second time around. We move 9 to the root, swap with 3, then swap with 5, until 9 reaches a leaf. And look, 1 and 2 came back out in order, and 3 is already waiting on top. Keep that little fact in your back pocket. If you extract the minimum over and over, the numbers come out fully sorted. There's a whole sorting algorithm hiding in plain sight, and we'll cache it in very soon. Here it is in code with the swaps right out in the open. Push appends to the end, then walks up while the child beats its parent. Pop min takes the root, moves the last element up, and sinks it. Watch it run as a value swims up the live heap, exactly as the highlighted line says. What if you already have a whole pile and you want a heap? Here's the key: the leaves, about half the nodes, are each a valid 1-element heap already. So we only need to fix the internal nodes, working from the bottom up. By the time we sift a node down, both its subtrees are already heaps. So one single sift cleanly fixes its whole subtree. And surprisingly, this is linear, not n log n. The cheap nodes pile up at the bottom, where half of them fall nothing and a quarter fall at most 1 step. Only a tiny few near the top fall far. So adding it all up, the total is proportional to the number of nodes. Building by inserting does the exact opposite, making the many cheap leaves travel the very farthest. That finally gives us Heapsort in 2 clean phases. Phase 1, build a heap, which is linear. Phase 2, extract the root over and over, each one a logarithmic sift. The total is n log n, the best any comparison sort can ever do. And it sorts in place with no extra array at all. Using a max-heap, you swap the root with the last element, then shrink the heap by 1. That maximum lands in its final slot at the back permanently. The sorted tail grows from the back as the heap shrinks until the whole array is sorted. So let's gather all the costs we already derived. Find min is completely free because it's just the root. Insert is a single walk, the logarithm. Extract is also a single walk, the logarithm. Build is linear, and Heapsort is n log n. Every walk costs only the height of the shallow tree. Step back and look at what we've actually built. A heap is the natural priority queue. An ordinary queue serves you strictly in arrival order. A priority queue throws that out and serves the most urgent next. The emergency room, the scheduler, the package router, all want the best first, no matter when it arrived. A priority queue needs exactly 3 things, and a heap gives all 3 cheaply. Add an item, which is just a sift up. Peek at the most urgent, which is free, simply the root. Remove the best, which is a sift down, so a heap is exactly what a priority queue is made of. So how do you actually spot a heap in the wild? Do you repeatedly need the smallest of a constantly changing collection? Just the next extreme each time and not everything fully sorted? Is there a priority that isn't a rival order, so if you've got 3 yeses, you reach for a heap? A few shapes should now light up for you instantly. The K smallest of a huge stream, where you just keep a heap of size K. Merging K sorted lists with a heap of the K front elements. Always grabbing the cheapest next step, the engine inside shortest paths. And scheduling by urgency, the extreme of a pile again and again while the pile keeps changing. 4 mistakes cause almost every broken heap out there. The first is mixing the index conventions together. The second is sifting toward the wrong child instead of the smaller one. The third is forgetting the stop condition entirely. The fourth is expecting a heap to be sorted, so the cure is to draw the array as a tree and check the one rule at every node. You master heaps by tracing the swaps on paper until they become pure reflex. Insert a handful of numbers, drawing every single sift up. Extract until empty, drawing every sift down, then build a fresh pile bottom up. Say which way the value travels and why, and then go pattern hunting. If you remember nothing else, just picture this. An almost complete tree packed into a flat array with every parent no larger than its children. You keep it valid with 2 short walks, sift up and sift down, and the minimum is always sitting right on top. It answers one question asked forever: what's the smallest thing here right now? Want to keep learning? Come find us at academy.rudewrite.com.